Back in chapter 5, we learned important area under curves fact number 1, which is we can find distance traveled by finding the area under the velocity curve as long as the velocity is positive. So now it's time to figure out, what does it mean? How do we find distance traveled if the velocity is sometimes negative? Well, remember what we learned about velocity back in chapter 3 or 4, that if velocity is negative, that implies motion is backward. So think of this example. I have a bumblebee. This is a beehive and the flower. I have a bumblebee flying back and forth between the hive and the flower. Sometimes the bee is flying from the hive toward the flower, and then sometimes the bee is flying from the flower toward the hive. So how does that change how we think about distance, to know that sometimes the bee is moving toward a goal and then moving back away from that goal? So if our position, if we want to think of the hive as position 0, I have this bee that travels 100 feet per minute for 2 minutes. It's a constant speed that the bee is flying at, so that's why I have a flat, horizontal velocity curve. Bee flies for 2 minutes. I could find the area under that part of the curve and figure out that he's gone 200 feet. If he then flies back to the hive another 200 feet and then flies to the flower again and then flies halfway back, one thing I can ask about is, what's the total distance that the bee has traveled? What would the odometer on its car say if it was, or what would its Apple Watch or Fitbit say, the distance it's gone? So it's going to have traveled, I'll change color here, 200 feet, this 200 feet, plus another 200 feet back, plus another 200 feet toward the flower, plus another 100 feet halfway back to its hive. So 200 plus 200 plus 200 plus 100, we would say the total distance traveled is 700 feet. But another thing that we could think about instead is what we call displacement. Displacement is the change in position relative to where you start. So if we have a hive here and a flower here, and I leave from the hive toward the flower and come back and go from there and come back, where is the bee relative to where it started? Well, it's 100 feet from the hive. So that's the displacement of the bee. And one way to compute that is to think of this 200 feet as positive toward the direction of the flower from its starting point, the hive. This next 200 feet is negative. It just gets us back to where we started. This 200 is positive toward the flower, and this 100 at the end, negative. So I could think of this as 200 minus 200 plus 200 minus 100, which gives a positive 100 feet displacement. So we're going to see lots of examples where we differentiate between those two ways of thinking about distance, and we'll find a way to use integrals to help us. So our two new definitions: displacement is simply area under the velocity curve, even if that velocity is negative. The positive areas, the areas above the x-axis, and the areas below the x-axis will cancel each other out in places and just give us the change in our position from where we started. So that's the same integral we've been writing. We've just always been assuming that our velocity was positive. This will work even if velocity is sometimes negative. It just gives us what we call displacement, change in position compared to where you start. So to find the displacement of the bee, I could integrate from 0 to 10 the velocity function if I wanted to know how far the bee got from where it started over those first 10 minutes. if I want to find total distance traveled, I have to figure out where the velocity is positive, find the areas under the velocity curve there and count them as positive. I have to find all the places where the velocity is negative, find the area under the curve, which is going to end up having a negative area, and then treat them as if they were positive so that they count. Like if you were exercising, you would want all of your steps that you walked forward to count. You would also want the steps that you walked backward to count toward exercise. But they don't count to help you if you're trying to go to someplace. Then moving backwards takes you away from your goal. So here's the easy notation. Most of the time, if you get asked this question on the AP test, it'll be a sort of a calculator scenario, and you can simply integrate over the time interval you care about the absolute value of the velocity function. So that lets the calculator do for you all that part of breaking up the integrand so that you could have the positive velocity parts and the negative velocity parts separate and treat them as if they were all positive. If you had to calculate total distance traveled by hand, it would be your job to stop and figure out where the velocity was positive. So I happen to have a graph, so I could tell the velocity was positive between 0 and 2, between times 6 and 8. And I could just integrate those. The places where the velocity is negative, I would have to integrate. I'm going to get a negative result because I have a negative velocity. And then I have to take the absolute value of those sections so that they would end up counting toward my total distance traveled. You will frequently on the AP test see questions about ending position. So your ending position depends on two things. It depends on where you start and the displacement. So expect to see problems where you'll have to find displacement. How far does something get as like a net get over a certain period of time? Don't forget that if you're asked about ending position, you have to consider where your particle started to. So here we have a velocity function, and we have several questions. So can we figure out, given this velocity function, when motion is forward, backward, and stopped? So where is velocity positive, negative, and 0? And then we're going to use those answers to help us figure out displacement and total distance traveled. And in the process, we're going to practice writing the integral notation for those values. So part A, this is a question we could have answered back in chapter 3 or 4. If I care about, when velocity is, I care when the particle is moving to the right, that's when velocity is positive. So really what I want is a sign chart for the velocity. So to make a sign chart for a quantity, I need to know when that quantity is equal to 0. So I'm going to start by figuring out when the velocity is 0. So 6 times sine of 3t. I need that to equal 0. I'm thinking of using the zero product property, but 6 is never equal to 0, so that's not going to help me get any solutions. I need to know when sine of 3t is equal to 0. So the way I solve trigonometric equations, I need to think of what I could sine so that the result is 0. Well, that's 0. Now, sadly, I don't have just the sine of t, I have the sine of 3t, but that's okay. So I need 3t to equal 0. So what should I sine to get 0 as the result? I need to sine 0. Well, that means what's getting signed needs to equal 0. So 3t equals 0 tells me that happens when t equals 0. The next time it could happen is if 3t equals pi, which tells me that t equals pi over 3. Now notice I'm only supposed to consider time values that are between 0 and pi over 2. So I'm going to try the next one. I'm not sure it's still going to fit. I could have 3t equal 2 pi, which would give me t equals 2 pi over 3, but that's outside of that range, so I'm not going to count that guy. So the times at which velocity is 0, r time 0. Let me delete that. And time pi over 3. All right. I'm going to put my endpoint in there too, pi over 2. Now the question is, for which of these intervals, and notice now I only really care about time 0 to pi over 2. So there's little extra pieces on the edge. I'm not going to even worry about trying to figure those guys out. I'm going to need to know if I pick a point in this section of the graph, will the velocity end up being positive or negative? And then I'll pick a point in that section. All right, so I'm going to test pi over 4. That's on my first interval. So that's going to be 6 times the sine of 3 times pi over 4. So 3 pi over 4, which is 6 times radical 2 over 2. I don't even need to simplify. All I need to do is notice whether that result is positive or negative. I found that to be positive. And since sine changes sign at pi over 2, sine of 3t is going to change sign at pi over 3. So this section here is going to be negative. So now I know if I care about the whole interval 0 to 2 pi, 6 times the sine of 3t will be positive between 0 and 0 and pi over 3, and will be negative between pi over 3 and pi over 2.